The music pulsed. Lights strobed. A crowd swayed on the dance floor of Temple, a trendy San Francisco nightclub. This was no ordinary Friday night, it was the quarter-of-the-century tech giga party. Anticipation crackled in the air. Suddenly, the music stopped. A spotlight pierced the darkness, revealing a figure on stage. It was a humanoid robot, the Phantom MK1. This wasn't a sleek, chrome-plated vision of the future. The Phantom MK1 was raw power personified. Standing 1.75 meters tall, it weighed 80 kilograms of advanced composites and alloys. Its movements were fluid, almost graceful, driven by powerful cycloid actuators. This was a machine built for war. The crowd, a mix of tech enthusiasts, venture capitalists, and social media influencers, erupted in cheers. They had just witnessed the unveiling of a new era, an era where the line between technology and warfare was becoming increasingly blurred. But beneath the surface of excitement, a question lingered. What did the rise of robots like the Phantom MK1 mean for the future of humanity? The company behind the Phantom MK1 was Foundation Robotics Labs, a startup founded in 2024 by Sanit Patak and Mike LeBlanc. Patak, a former fintech entrepreneur, brought his business acumen to the table. LeBlanc, a former U.S. Marine and co-founder of a security robotics company, provided the military expertise. Their goal? To revolutionize warfare with advanced robotics. They believed that robots like the Phantom MK1 could save lives by taking humans out of harm's way. They envisioned a future where wars were fought by machines, not men. Their ambitions were lofty, their timelines even more so. Foundation Robotics Labs aimed to ship over 40 Phantom MK1 units by the end of 2025. By 2026, they planned to increase production to 10,000 units, followed by 20,000 units in 2027. Their ultimate goal was to achieve $1 billion in annual recurring revenue and establish bases in Antarctica, on the Moon, and even on Mars. The unveiling of the Phantom MK1 was just the first step towards realizing their vision. The Phantom MK1 was a marvel of engineering. Designed to be the ultimate war machine, it combined the latest advancements in robotics and artificial intelligence to create a formidable presence on the battlefield. Its advanced cycloid actuators combined the power of hydraulics with the precision of modern engineering. These actuators were the heart of the Phantom MK1, allowing it to perform tasks that were previously thought impossible for robots. The integration of electric motors into its design further enhanced its capabilities. These motors provided the necessary efficiency and control, ensuring that the Phantom MK1 could operate smoothly and effectively in various conditions. This combination of power and efficiency gave it incredible strength and agility. The Phantom MK1 could lift heavy objects with ease, demonstrating a level of dexterity and power that was unmatched by any other robot of its kind. With a peak torque of 160 Newton-meters, it could lift heavy objects and deliver devastating blows. This made it an invaluable asset in both combat and non-combat scenarios, where strength and precision were paramount. The Phantom MK1's ability to perform heavy lifting and engage in combat training scenarios showcased its versatility. It was not just a machine of war but a multifunctional tool that could adapt to various roles as needed. Its sensors and cameras provided 360-degree situational awareness, allowing it to operate effectively in complex environments. These sensors were crucial for navigation and threat detection, ensuring that the Phantom MK1 could respond to any situation with precision. This situational awareness was a game-changer, allowing the Phantom MK1 to navigate complex environments with ease. Whether it was a dense urban landscape or a rugged natural terrain, the robot could adapt and overcome obstacles. It could navigate uneven terrain, climb stairs, and traverse obstacles that would be challenging for even the most advanced robots. This capability made it an ideal candidate for missions that required mobility and adaptability. The Phantom MK1 could even run at a human-like gait, a feature that was particularly useful in scenarios where speed and agility were crucial. This ability to move quickly and efficiently set it apart from other robotic platforms. The Phantom MK1 was designed to be a versatile platform. Its creators envisioned a machine that could perform a wide range of tasks, from combat operations to humanitarian missions. This versatility was one of its key strengths. While its creators envisioned it primarily for military applications, the potential uses for the Phantom MK1 extended far beyond the battlefield. Its advanced technology and robust design made it suitable for a variety of roles. It could also be used in a variety of civilian roles, such as search and rescue, disaster relief, and even industrial automation. These applications highlighted the robot's adaptability and potential to make a positive impact in non-military settings. In disaster relief scenarios, the Phantom MK1 could navigate hazardous environments to locate and assist survivors. In industrial settings, it could perform tasks that required precision and strength, improving efficiency and safety. It was a testament to the growing convergence of military and civilian technologies. The line between these two domains was becoming increasingly blurred, as innovations in one area often found applications in the other. The technology behind the Phantom MK1 was based on research acquired from Boardwalk Robotics, a company known for its pioneering work in humanoid robotics. This research provided the foundation for many of the robot's advanced features. Boardwalk Robotics, a Florida-based company, was renowned for its Alex humanoid robot. The expertise and knowledge gained from developing Alex were instrumental in the creation of the Phantom MK1. Foundation Robotics Labs had acquired Boardwalk Robotics in August 2024, giving them access to years of research and development in humanoid robotics. This acquisition was a strategic move that significantly boosted their capabilities. The combined expertise of both companies resulted in a robot that was not only advanced, but also highly adaptable. The Phantom MK1 was a testament to what could be achieved when cutting-edge technology and innovative thinking came together. Section 4. Silicon Valley embraces the battlefield. The entrance of Foundation Robotics Labs into the defense sector was part of a larger trend. This trend has been gaining momentum over the past decade, as the lines between civilian and military technologies continue to blur. The innovations that once powered consumer electronics and social media platforms are now being repurposed for the battlefield. Tech companies, once hesitant to get involved in military applications, were increasingly embracing defense contracts. This shift marks a significant departure from the early days of Silicon Valley, when many tech pioneers were staunchly opposed to any form of military collaboration. The change in attitude is not just about financial incentives but also about the evolving role of technology in society. This shift was driven by several factors. One of the most compelling reasons is the rapid advancement in technology itself. As artificial intelligence, machine learning, and robotics have progressed, their potential applications in defense have become too significant to ignore. The ability to develop autonomous systems that can operate in complex environments has opened new avenues for tech companies. Firstly, the increasing demand for advanced technologies in modern warfare made the defense sector a lucrative market. The need for cutting-edge solutions in areas such as cybersecurity, surveillance, and unmanned systems has created a fertile ground for tech companies to expand their horizons. The defense sector's appetite for innovation is insatiable, and tech companies are eager to meet this demand. Governments around the world were pouring billions of dollars into military AI, robotics, and autonomous systems. This influx of funding has not only spurred innovation but also created a competitive landscape where tech companies vie for lucrative contracts. The collaboration between government and private sector has become a driving force behind many technological breakthroughs. Tech companies, with their expertise in these areas, were well positioned to capitalize on this demand. Their deep knowledge of software development, data analytics, and hardware design makes them ideal partners for defense agencies looking to modernize their capabilities. The synergy between tech companies and the military has led to the creation of sophisticated systems that were once the stuff of science fiction. Secondly, the growing geopolitical instability and the rise of new global powers created a sense of urgency around national security. The increasing complexity of global threats has made it clear that traditional defense strategies are no longer sufficient. Advanced technologies are now seen as essential tools for maintaining a strategic advantage in an unpredictable world. Tech companies, once driven by libertarian ideals and a desire to not be evil, were now confronted with the reality of a world where their technologies could be used for both good and evil. The ethical dilemmas posed by this dual-use nature of technology have sparked intense debates within the industry. Companies are grappling with the moral implications of their work, even as they push the boundaries of what is possible. Companies like Meta, OpenAI, and Google, once vocal in their opposition to military contracts, had all shown a willingness to work with defense agencies. This willingness is often framed as a pragmatic response to the changing landscape of global security. By engaging with the defense sector, these companies aim to ensure that their technologies are used responsibly and effectively. This shift was a sign of the times, reflecting the growing convergence of technology and warfare. As the world becomes more interconnected and the pace of technological change accelerates, the collaboration between Silicon Valley and the defense sector is likely to deepen. The future of warfare will undoubtedly be shaped by the innovations emerging from the tech industry, making this partnership more crucial than ever. Section 5. Bridging the Gap. Nvidia and Carnegie Mellon's ASAP framework. While robots like the Phantom MK1 were impressive feats of engineering, their real-world performance often fell short of expectations. These robots, designed with cutting-edge technology, showcased the potential of robotics but also highlighted the significant gap between theoretical capabilities and practical applications. Engineers and researchers faced numerous challenges in ensuring that these robots could perform consistently and reliably in real-world scenarios. One of the biggest challenges in robotics was bridging the gap between simulation and reality. In controlled environments, robots could execute tasks with precision, but once outside these controlled settings, their performance often deteriorated. This discrepancy was a major hurdle for the robotics industry, as it limited the practical deployment of robots in everyday tasks and complex environments. Robots trained in virtual environments often struggled to replicate their performance in the real world. The simulations, while sophisticated, couldn't account for every variable and nuance of real-world conditions. This led to robots that were highly efficient in virtual tests but faltered when faced with the unpredictability of real-life situations. The need for a solution that could align these two worlds became increasingly apparent. To address this challenge, Nvidia, a leading manufacturer of graphics processing units, partnered with Carnegie Mellon University to develop the ASAP, or Aligning Simulation and Real Physics Framework. This collaboration brought together Nvidia's expertise in high-performance computing and Carnegie Mellon's pioneering work in robotics. The goal was to create a framework that could significantly enhance the accuracy of robotic simulations, making it easier to transfer skills learned in virtual environments to the real world. ASAP used machine learning to improve the accuracy of robot simulations, making it easier to transfer skills learned in virtual environments to the real world. By leveraging advanced algorithms, ASAP could analyze and adapt to the differences between simulated and real-world conditions. This meant that robots could be trained more effectively in virtual environments with a higher likelihood of successful real-world application. In tests, ASAP reduced motion errors by 53% compared to previous methods. This significant reduction in errors demonstrated the potential of the framework to revolutionize the field of robotics. Researchers observed that robots trained with ASAP were more consistent and reliable in their movements, which was a crucial step towards their practical deployment in various industries. The framework was tested on a G1 humanoid robot, a research platform developed at Carnegie Mellon. The G1 robot served as an ideal testbed due to its advanced capabilities and the complexity of tasks it could perform. Researchers used the G1 to evaluate the effectiveness of ASAP in real-world scenarios, pushing the robot to its limits to gather comprehensive data. The robot was tasked with performing forward jumps over 1 meter, a challenging task that required precise control and coordination. This task was chosen because it represented a significant challenge in terms of balance, timing, and power. Successfully executing such a maneuver would be a strong indicator of the framework's effectiveness. While the ASAP framework showed promise, the testing process was not without its hiccups. Engineers encountered several issues, including software bugs and unexpected hardware failures. These challenges underscored the complexity of developing advanced robotic systems and the importance of rigorous testing and iteration. Hardware issues, including motor overheating and damage to two test units, highlighted the challenges of pushing the limits of robotics. These incidents served as valuable learning experiences, providing insights into the durability and resilience of robotic components under strenuous conditions. The team used these insights to make necessary adjustments and improvements. Despite these setbacks, the development of ASAP was a significant step towards improving the real-world performance of robots. The successful implementation of the framework in various tests demonstrated its potential to bridge the gap between simulation and reality. Researchers and engineers celebrated these milestones, recognizing the long-term impact of their work on the future of robotics. Nvidia and Carnegie Mellon released the ASAP code open source on GitHub, encouraging further development and collaboration within the robotics community. By making the code available to the public, they aim to foster innovation and accelerate advancements in the field. This move was welcomed by researchers and developers worldwide who saw it as an opportunity to contribute to and benefit from the collective progress in robotics technology.